Hi, it's me, Mr. Summers. We're looking at balancing reactions today, and I've got the notes here. I'm going to breeze through them quickly and just get to the balancing so we can give it a try. And if you missed today, hopefully this will help you out. So we finished naming and formula writing, so now we're looking at putting those elements or those compounds together and making them into sort of like chemical sentences, and that's what we call a chemical reaction. So a chemical reaction looks like here in the middle. We've got the A element or compound plus the B, and then the equivalent of like the equal sign in math makes C and D products. So we call the reactants the things you start with, the products the things that you make, and in the middle the words would be like makes or produces or yields. So you don't say equals, you'd say like A reacts with B to make C and D or to produce C and D. Sometimes when reactions are written out, they'll have these state symbols here at the bottom. That just tells you the state of the element or compound that's in, so solid, liquid, and gas. And then one of the most common ones actually is aqueous, which we'll get to second semester, but aqueous just means you dissolve that compound in water. A lot of times the reactions take place when you dissolve two solid compounds in water and then mix the water together. So if I was reading this reaction here for the sodium, I would say that solid sodium reacts with chlorine gas to make liquid sodium chloride. Even though that's not really true, that's just like what the state symbols mean. Okay, so as we look forward, I just rewrote the reaction here. When we have the reaction written this way, like we have there, it's not technically a correct reaction. This is called an unbalanced or skeleton reaction. It shows that the chemicals are involved, but not necessarily in the correct ratio. Kind of like saying if you wanted to make a cake, we would need flour, sugar, and water. No, that's not right. Flour, sugar, milk, and something else. I can't remember. Eggs. Flour, sugar, milk, and eggs. I'm not telling you how much of each of those things. I am telling you that's how you make a cake, but I'm not telling you how much. The same thing with this unbalanced reaction. I'm telling you that sodium will react with chlorine to make sodium chloride, but I'm not telling you exactly how much. So we fixed that problem by balancing the reactions. And so balancing reactions addresses something that's very critically important called the law of conservation of mass, which means that the mass of the reactants must equal the mass of the products. And we have a problem when we look at this reaction is that I start with one sodium and I end with one sodium, and that's super cool, but I start with two chlorines and I only end with one chlorine, and that's technically impossible. I just can't make one chlorine go nowhere. Okay, so we put numbers in front to balance, like I've written here in orange. The only thing you can do when you balance is put numbers out in front of things that I've written. Oops, that's not one. Written right here. And you can put numbers in there, and you can only use whole numbers, and that's how you balance. And each number distributes. So if I were to write like 7 here, it'd be 7 times 2 for 12 chlorine, or 14 chlorine, geez. If I put a 7 there, it'd be 7 sodium and 7 chlorine because it distributes. So in front, it distributes everything. If the number is behind, it only distributes to that one particular element, okay? So if there was a 2 here, it'd be 14 sodium, and then it would only be 7 chlorine. Okay, so whoopsies. So let's get rid of all that, show you how to do it. There's sort of two modes of thought here. The first, and I think maybe the easiest for most people as they're starting, is to make like a table of reactants and products, okay? And in this first reaction, we've got sodium and we've got chlorine. On the reactant side, we've got 1 sodium and 2 chlorine, so 1 sodium, 2 chlorine. On the product side, looks like we have 1 of each, 1 sodium and 1 chlorine, so 1 and 1 there on the product side. And you want to make them equal. So if I start with 1 sodium, I should finish with 1 sodium. If I start with 2 chlorine, I should finish with 2 chlorine. And really, in this case, there's only one place to start because you can see I've only got 1 sodium there, and I've got 1 sodium there, so I'm not going to start there. Instead, I'm going to start at chlorine, which I have 2 there, and I only have 1 here. So I'm going to put a 2 in front. Now, reactions or balancing is a lot like this. When you put a 2 in front, it messes everything out, right? So I got 2 chlorine, which is great. So you can reflect that here on your little table. But I also gave myself 2 sodium, which is not cool. So I have to go back to the other side. And here, if I'm keeping track on my table, back to the other side there, and you say, oh, okay, well, I need to have 2 sodium now, so I put a 2 in front there, and now I've gotten them both to be 2 on the other side. Now, they're both the same number, so that doesn't make a difference. It's just a coincidence here. So I've got 2 sodium, and I've got 2 chlorine each on both sides. If the bottom number was like a 3 or whatever, you'd have to make it a 3, so 3 and 3, but okay, but they don't always have to be the same number is what I'm trying to say, but I'm saying it very poorly because that's kind of my bit. But in this case, they're both 2 and 2. Okay. I put a lot of extra things in there just to help you like read it, so I don't need that or that or this or this or this or this. Okay. The table's there, and you can use the table, but for speed purposes of this video, I'll drop the table. But please use the table if it helps you be more successful at these. That's what we're looking for. But I appreciate that. So, okay, so in the next one, again, you can pick anywhere to start. You only put numbers in the lines that I've drawn there for you, and they have to be whole numbers. That's it. Those are the rules. So it's pretty straightforward. And you kind of bounce back and forth when you do it. So if I was looking at this one, I'd just start at the beginning, I guess. 2 nitrogen here, but I only have 1 nitrogen there, so I put a 2. Okay, that equals the nitrogen on both sides, but this 2 distributes. So 2 nitrogen, yay, but now I have 6 hydrogen, boo, right? There's a 3 there, so 2 times 3 is 6. So I got to make this one a 6, but there's already a 2 there. So the number I put in front is a 3. So this is balanced when and that's the correct ratio in which the reaction happens. Again, I've added a lot of circles and crabs for you to see, but in reality, that's your answer right there. Okay, table is great. If you want to make a table, please do. But just for speed, I'm not going to be making a table right now. You can always go back and check. And if it doesn't work out, you can start somewhere else too. That often helps. If like starting at nitrogen wasn't working out for you, just nuke it. Start over, start at hydrogen, see how far that gets you. So in this one, the ratio then is like you're saying that it takes 1 nitrogen molecule to react with 3 hydrogen molecules to make 2 ammonia molecules. That is what is going on when I say the coefficients are 1 and 3 and 2. A couple more for our brief video here. Sometimes the one that looks more complicated, you have polyatomics, you can treat them as one thing. So you can say this is 1 SO4 here, and I've got 1 SO4 there. As long as they're the same on both sides, it just saves you a little bit of time. And I've got 1 PO4 there, and I've got 2 PO4s there, right? So it just helps you to balance if you can consider them one thing. Ideally, you want to balance each of the elements individually, but when they're the same like this on both sides, it just saves you a little bit of time for balancing purposes. So you can pick anywhere to start, which is the nice part about this. I might as well pick magnesium because that's the first one. If I look at magnesium on this side, there are 3, but there's only 1 here, so I'm going to write a 3. That 3 distributes, okay? So now I've got 3 sulfates, so I bounce back over to here. On the sulfate side, I only have 1 sulfate. SO4 is the thing, so I don't have 4 of them. That is what sulfate's called. So I put a 3 in front of there, okay? That 3 gives me, again, you bounce back and forth, right? So 3 times 2 hydrogens, that's 6. So I'm gonna make this one a 6 on this side by putting a 2 there because 2 times 3 is 6. But that gives me 2 phosphates, and guess what? I already have 2 phosphates. So again, you're bouncing back and forth on these to sort of get the correct number, and I'm just drawing all this extra garbage to help you see where I'm going. But in the end, you're saying that 3 magnesium sulfates reacts with 2 hydrogen phosphates to make 1 magnesium phosphate and 2 hydrogen sulfates, okay? Last one we'll look at for today. Sometimes there are going to be ones that are called combustion reactions. This is a combustion reaction when it starts with C's and H's right there. Let's make a better arrow for America. There you go. So when it has C's and H's right there and then it reacts with oxygen, that's called a combustion reaction. This is what happens when you drive your car, or in this case, this is what happens when you light a propane gas tank. So if you're cooking on a grill and it's got propane, or if your home is heated by propane, if you live out in the sticks somewhere, this is what we call a combustion reaction. So this also makes a lot of heat, but the heat's not represented there on the reaction. So for these, it's best to balance alphabetically. If you leave oxygen for last, you can put any number you want there, which is really convenient. So that's why we leave it for last. Just a helpful tip, if there's any element that's by itself, leave it for last. It just makes balancing a little bit easier. So if we've got 3 carbons here, I'm going to put a 3 there. That gives me 3 carbons. Now the temptation is to move on to oxygen, but reserve that for later. So we go back to hydrogen here, and I've got 8. I've got 2 there, so I'm going to put a 4 there because 4 times 2 is 8. Now here's the trick for combustion reactions. You have to total up all the oxygens on this side. So the oxygens from here and the oxygens from there have to be equal to the oxygens that are right there. Okay, that's how the law of conservation of mass works. So here on this side, erase here. Here I've got 3 times 2, that's 6. And here I've got 4. 4 times 1, that's 4. 6 plus 4 is 10. So I want to make this one 10, so I put a 5 there to make it 10. So all balanced, you're saying that this reaction is 1 propane molecule reacts with 5 oxygen molecules to make 3 carbon dioxides and 4 water molecules, and of course a whole bunch of heat for you to cook your hamburger or whatever. So there's the brief on balancing. If you missed today, very short notes. Hopefully you get these notes into your note guide so you can stick along with us as we continue learning about reactions. Okay, this has been super fun. Bye.